CPU, the central processing unit, reads and executes the instructions of programs. So when we write code, ultimately what we are doing is creating a series of instructions for the CPU to run. These instructions are expressed in binary code, and each instruction tells the CPU to do some very small amount of work. Something like, say, copy this data from this part of memory here to that other part of memory, parts of memory, and add them together as numbers. Generally, these instructions perform very small basic operations, and at first it can be quite baffling to imagine how these very small basic operations combine to do the sorts of interesting behaviors you see in programs like, say, video games. As you progress through this series, however, this should become less mysterious. The memory of a computer is the location where the data and code of running programs are stored. When the CPU runs a program, it reads the instructions from memory, and during the execution of that program, if the program needs to store some more data, it can store the data in memory as well. The I/O of the system, the input-output, does not refer to one component, but rather basically to everything else other than the memory and the CPU. Systems typically have many input-output devices. For example, a monitor is an output device, a keyboard and a mouse, those are input devices. A storage drive like a hard drive, that's both an input device and an output device because data goes both in and out. So the relationship between these three parts, the CPU, the memory, and the I/O devices, is that the CPU is in control. The CPU does its job by reading instructions found in memory, and those instructions may tell the CPU to send instructions to input-output devices, effectively telling those input-output devices what to do. While a CPU will not execute instructions directly from an input-output device, typically what happens is that programs are loaded from a stored file, like say on a hard drive, then copied into memory, and then the CPU executes that program in memory. So in a sense, CPUs do execute instructions off of input-output devices, they just don't do so directly. The reason for this, as we'll discuss later, mainly has to do with performance. The CPU typically can read data from memory much faster than it can read from input-output devices, like say a hard drive. Now, as we mentioned, the instructions which a CPU executes are binary codes. They're just a series of zeros and ones. Or, more accurately, they're a series of electrical impulses in one of two states, and we represent these states with the symbols 0 and 1. The obvious problem is that these binary codes are extremely unfriendly for humans. Humans just aren't very good at reading and writing a long series of zeros and ones. Writing a program as a bunch of zeros and ones would be extremely tedious. The solution to this problem is to create programming languages. In a programming language, the programmer writes code in a form that's more human-friendly. It's of course not a human language like English, but rather a formal language, a language with formal rules specifying exactly how the code must be written to be understood by the machine. A computer, however, cannot directly execute such code, because the code is written as a bunch of text instead of binary instructions. So the text written by the programmer has to be translated into binary instructions, an actual runnable program. Programs which do this translation are called compilers and interpreters. The distinction between compilers and interpreters we'll discuss in a later video. For now, we'll just use the generic term translator. Now, you might be wondering where translators come from. Well, of course, originally people had to write these translators in machine code directly, but once translators existed, people could use them to write subsequent translators. So now that you hopefully have a concept of what a programming language is, we can introduce an elementary programming language. This language is in fact one I myself made up, and I call it Pidgin. I created Pidgin explicitly for educational purposes by making it as productively simple as I believe possible. This doesn't mean, however, that Pidgin is unrepresentative of real programming languages. All of the concepts you'll learn with Pidgin directly correlate to the most essential features of real programming languages. When we write code in a programming language, we write it as text, and this code is called the source code, so called because it's the source from which the translator produces actual runnable programs. The first rule to learn about Pidgin code is that the hash sign, sometimes called the octothorpe or the number sign, that denotes the beginning of a comment. A comment in source code is simply text which is ignored by the translator. All languages allow for comments so that programmers can write notes of code that describe anything about the code which isn't apparent to a human reader. Notice that when I show a comment, I'll highlight it in orange so that you can more easily distinguish it from actual code. The term value in programming generically refers to some piece of data. So a number value like the number 3, that's obviously a value, a piece of data. Values in programming, though, may come in many different types, not just numbers. So in Pidgin, for example, we have numbers, we have what are called strings, we have what are called booleans, and later on we'll introduce a couple of additional types. A string, quite simply, is a piece of text. It's a sequence of text characters. So say in code you wish to store someone's name. That name would be stored as a string value. The Boolean data type actually has just two different possible values, the values true and false. Booleans come in handy for situations like, say, your program has options that can be enabled or disabled. The enabled state would be represented by the Boolean value true, while the disabled state would be represented by the value false. If you're wondering about the odd name, Booleans are named after the 19th century English mathematician George Boole, who invented binary algebra and algebra logic. So it makes sense that we name the data type for true and false after him. In the text of our source code, when we express a specific value, that is a literal. It is a value literally written in text. So, for example, when you write a number in digit, it can just be a simple positive number, like here 3, or a negative number, like say negative 17.4, or a number with a fractional component, a decimal point 8.93, or a negative number with a decimal point like negative 0.88888881. When we express Boolean values as literals, we write them simply in lowercase, true and false. When we write a string, we enclose the characters of the string between double quote marks. So here in the top example, that's a string containing a sequence of characters starting with a capital R, then period, then space, capital N, lowercase I, lowercase x, O, N. So one thing to note here is that uppercase letters are different characters than lowercase letters. The uppercase N is a different character than the lowercase n. Also note that a space is itself a kind of character. It's part of the data of the string. In the second example from the top, that's a string with just a single character, a capital T. The third string down reads elementary, comma, my dear Watson, and then the last string at the bottom consists of just a single character, a percentage sign. So that's how we write number strings in Booleans. There is, however, one more literal for the special value null. The null value, which you can sort of think of as another data type with just one possible value, is used to represent nothing. It's effectively used as a placeholder, meaning there's nothing here. Note that the null value, like true and false, is always written in all lowercase. When we write a string literal, there are some characters which can only be included by using what's called an escape sequence. For example, the double quote mark character, you can't simply put that in the middle of a string because the double quote mark character denotes the end of the string. Consequently, to include the double quote mark, we have to escape it, meaning we have to put a backslash in front of it. And that indicates to the language that the following character, the double quote mark in this case, is not meant to denote the end of the string. It's just meant to denote a double quote mark character in the text data. So in the string literal at the top here, the first character of the string is simply a single double quote mark character. The backslash followed by the double quote mark, those two characters together represent an escape sequence. They represent one character in the text data, a double quote mark. In the second string, where we see backslash n, that is an escape sequence representing the new line character. The new line character, as the name implies, is used to denote where a new line should start. So the text in this example reads hello, comma, and then on the next line, world, period. Now, of course, what we see here is written all on one line, but the idea is that a program that renders text should render this text on two successive lines. So just be clear, in the string data, we have this new line character to indicate the intention that there be a new line there, but it's ultimately up to whatever code renders a string on the screen or a printer somewhere. It's up to that code to represent the new lines, to draw the character after the new line on the next line down. In our code, however, we must write string literals always on just one line. We can't continue them onto the subsequent lines, so the opening and closing double quote mark of a string literal will always be on the same line. Finally, in the bottom string, the escape sequence backslash backslash is used to denote just a single backslash character. So the text data of the string actually reads C:\\, backslash blah, backslash blah, backslash blah. The reason we have to use an escape sequence to denote a backslash character is because the backslash character itself is used to denote the start of escape sequences. So if we just wrote single backslashes here, then the backslashes would appear to the language to denote the start of escape sequences, but that's not what we intend here, so we write a pair of backslashes just to have a single backslash character. The basic units of action in our code are called operations, and just like in mathematics, an operation is something which takes input values and then returns an output value. Like say, an addition operation where the inputs 3 and 5 returns the value 8. In an operation, the part which specifies which operation to perform is called the operator. Like say, the plus sign in an addition operation, that's the operator. The input values to the operation, those are called the operands. So here's an example addition operation as you used to see it in mathematical notation. The plus sign is the operator, and the operands are 3 and 5. In Pidgin, however, we use a slightly different style of notation for operations called prefix notation. The notation you're familiar with from mathematics is called infix notation, so called because the operator is infixed between the operands. In prefix notation, the operator is placed in front, and then the operands are listed afterwards. Another change we make in Pidgin is that the operators for common operations are not denoted by